Regardless of what you heard, quantum does not mean futuristic. It means discrete, or really countable. And when you hear it, you shouldn't think big or fast, but very small. Now, since Einstein, physicists have known that matter and energy don't act like baseballs and beams at the smallest scales. Instead, things follow a unique set of rules that seem counterintuitive if you apply them to baseballs and beams. Imagine if a baseball acted as a beam of light when a pitcher threw it, or if you could catch a beam of light like a baseball. But that's just the start, and we will be getting into baseball. So, as weird as these rules may seem, they describe why our universe acts the way that it does. They explain how solar panels convert light into energy. They explain why the structure of different molecules fight diseases or get us sick. Really, they explain why things are the way they are. But what if we wanted to design new things using those rules? What if we wanted to create new batteries, new drugs, fuels, or even new materials for spacecraft? We just have to harness those rules. But that is an entirely different challenge and the grand problem that we're trying to solve by building quantum computers. Welcome to the Coherence Times, where we dive into the science and the story of quantum computing. I'm your host, Ryan Mandelbaum. Every other week, I'll be sitting down with researchers, technologists, and thought leaders to unravel the incredible challenges and breakthroughs shaping this generational technology. So, whether you're a tech enthusiast, an industry leader, or just somebody who's curious about how quantum computing might change the world, well, you're in the right place. Together, we'll demystify the concepts, bust the myths, and explore not just how quantum works, but how it can work for you. So today, I'll have Jamie Garcia, Director of Strategic Growth and Quantum Partnerships on to talk us through what quantum means and how we might harness these rules to simulate the world we live in. Hello, Jamie. So tell me a bit about what you do.
I'm Jamie Garcia. I'm, like you said, I work in IBM Quantum. I work with a lot of our big partnerships and universities and things like that. My background is actually, I have a PhD in chemistry. So I would call that applied quantum mechanics, if you will. And I currently work with a lot of people from a lot of different backgrounds. On quantum computing and applying it to different problem sets. So that's what I do in a nutshell. We can go in depth on other parts of that later.
Awesome. Well, we're going to go into the deepest depths because we're going to start with my first question, which is simply, what does quantum mean?
Oh my gosh, what does quantum mean? I have a 4-year-old daughter, and one of the things that she learned very early on when she was 2 years old is what's the opposite of classical? And it's quantum is the answer. So quantum is basically what describes, nature. Quantum is basically the rules and principles that nature follows. And when we talk about quantum, what we're really describing in that instance is subatomic particles. So things like electrons and photons. Um, so in a nutshell, that's quantum. Although you do see it everywhere. But that's what I think of when I think of quantum.
Got it. So it's just little stuff works different than big stuff.
Yes, absolutely. So there's the things that we have like interaction with on a daily basis that I think we develop a lot of intuition for as we go through our lives in the world. Um, Mass and like the wall is solid and like things like that. When you start getting into the quantum world and thinking about quantum atomics, it's not as intuitive anymore. It really is sort of the description of how nature at its most fundamental and, yes, tiny scale works.
How did scientists first find out that small things and big things work differently?
I think that there was a lot of behavior that wasn't necessarily easy to describe that we saw in nature. And so, for example, the behaviors of molecules and things of that nature. I mean, coming from my background, there wasn't always a very good reason to describe like why they were doing certain things, why they were reacting certain ways, and things like that. And so I think once you actually started looking closer at the behavior of physical systems, you started seeing some inconsistencies with what, like I said, the world that we're so intuitive and have normal everyday interactions with behaves. So that's really, I think, where a lot of this started being uncovered is when we really started digging deep into things that were physical.
Maybe we can just start then going through some of those differences. So, what are kind of the basics, like how particles work differently than, a baseball?
Yeah, so I think there's some things that, like I said, are very non-intuitive. So the fact that particles behaves as both particles and as waves is a very unintuitive thing to think about. How they interact with each other, different kind of things that you can do, like that we leverage all the time for quantum computing. For example, entanglement is not an intuitive thing to think about at all. That you can have two particles that are so interconnected and so intertwined that if you know something about one, you by default know something about the other, and in a way that's faster than the speed of light. I mean, these are all again like things that we have experimental evidence that they exist, and then when we start applying quantum mechanics to computation, those are the levers that we then use to actually be able to program quantum computers. But yeah, not not intuitive at all and very, very different behavior than what we experience on a day-to-day basis.
Got it. So, I mean, the first one I guess we got these baseballs that are traveling like waves. Easy peasy. Looks like a it's like a baseball, but when you're throwing it, it's like more like a light wave, but
Uh-huh.
when you catch it, it's a baseball again. So intuitive enough to if I was the size of an atom.
Uh-huh. Right. Right.
Right. But not actually intuitive because if the speed at which I throw the baseball is not a continuous thing, I can't throw it at like 1 or 2 or 1.5 miles an hour. I can only throw it in sort of like energy quantized things, right? Like 1 mile an hour, 2 mile an hour, 3 mile an hour.
Right, like discrete energy levels. Yes, exactly. There's no in between. You can't sit in between the energy levels. Yes.
Perfect. And then if I throw this baseball and you try and catch it, I actually can't tell you how fast it's moving or where it is at the same time. So when I throw it, this baseball leaves my hand and it's gone completely. If I want to measure the speed, then I have no idea where it is. So at least the radar gun works. But if I want to catch it, well then the radar gun doesn't work.
Right. Yeah, and I think that that's really getting at the heart of it. So, you're describing some of the things like I think in the backdrop there's experiments that are famous that, capture this behavior and tells us that this is the way that, subatomic particles behave. So the double slit experiment is one that we all I think did as a part of anyone who had a science degree did as a part of your undergraduate education and your physics class to kind of see how like you can get interference patterns when you pass a laser beam through two slits in a piece of paper, right? And then have it projected onto a screen. So that's, definitely one. And then, obviously the experiments where you actually create a Bell state, which shows that particles are entangled. That's another one. And then the Heisenberg uncertainty principle, which is what you're talking about, which is like you cannot have the these particles are so interconnected that you can't measure one thing, and have like a very accurate or precise measurement of the other thing at the same time. So momentum, for example, and spin, for example. So those are the kinds of things that I think, again, it's true. We know that nature behaves this way, but it's just not something that I think, unless you go to that level of depth, you're ever going to experience.
I'm trying to see if I need baseball analogies for double slit experiment and Bell experiment. So baseballs and double slits, like I'm throwing these baseballs at the door, and it's like one of these double doors. And if I throw one baseball, it just acts like I threw a baseball. But if I throw like a bunch of baseballs, it looks as if they all picked selected almost like a stripe of baseball landing places, even though I just threw them at a double door. Okay, right. Okay. And then Bell experiment, I'm at a loss with this one because this one truly is the baseballs don't really act like this.
Yeah, so and I think yeah, exactly. I mean, this is just basically a way of showing that you're able to get non-classical behavior out of certain, in certain situations and scenarios, right? And it really I think shows a deviation from what you would expect if you were behaving classically. Um And this is one of the first things usually that we teach people when they start quantum computing is you create a Bell state. And that's one of like the first, I would say like experiments that you can try on a quantum computer where you actually are, people start realizing that this is behaving fundamentally differently from something that, like my laptop, for example. Um, so I think that that's a really important one. I mean, the all of these collectively together are sort of serve as the basis of what we do for quantum computing. And then again, like, we have things like superposition too. So we already sort of described this idea of like interference. That's definitely like something that you can leverage as a part of like programming a quantum computer. Entanglement, so spooky action at a distance, is probably, in my experience, one of the harder things for people to wrap their heads around. So the idea that you can have like subatomic atomic particles that are described by a single wave function. What does that mean? That means that no matter how far apart they are in the universe, I mean, you can have them galaxies apart, right? And they would still be entangled. They would still have this behavior where they're linked to each other in such a way that they will never be fully separated. And then superposition, I think, is the other one, right? Where you can actually drive, qubits to be in a superposition of states, which again is kind of hard to wrap your head around because it's described mathematically as a linear combination of states. But what does that mean? It means that it's a little bit of a one state and a little bit of a zero state at once to varying degrees, right? And so, that's another thing, like, people like to say it's, all the states all at once. That's not really true. It's a black box, that's true, but, like, you have this kind of combination of states, described. Yeah, mathematically.
Okay, so I got one more baseball thing, and then I think we can get it going. But I just want to make sure that this is my entanglement baseball thing. All right. So we're throwing baseballs again, but now the baseballs, they could be any color, but we're only gonna let them be red and blue. I got two baseballs. I got a red baseball and a blue baseball. Now, when I want to when these baseballs get put together and touch each other, they turn purple. They can be a little more on the red side or a little more on the blue side, but now they're both purple. Now I put both baseballs into some person's pocket, you and me, and we walk to the other side of the stadium. And then I look at my baseball, and then it's either red or blue, and that is it. And, statistically, if we do this a bunch of times, then, based on whether it was slightly more red or blue, the two baseballs together, then we're gonna have more red or more blue on one of them. Whatever. They're only red or blue. They can't be anything else, right? Because they're not everything at the same time. They're just either red or blue. And then this is the part that, you said spooky action, God don't play dice. And this is the part that, okay, so instantly, right? Oh my goodness, it's instant. Your baseball's red, my baseball's blue. But actually, it's not instant. It is technically instant, I suppose, but we didn't know that the baseballs were red and blue until I called you on the phone and said, all right, what color's your baseball? So it technically the information didn't travel faster than speed of light because I had to do a classical phone call to you to ask what color your baseball was. Am I right?
Okay, this is like I like the colors of the baseball. This is an interesting analogy. I dig it. I like that it can be more red or more blue. That's kind of like, the idea of superposition is like you have more of a one or a zero, right? And the red is the one and the blue is a zero state, whichever. And you're absolutely right. Like the measurement is kind of the key. Like this whole idea of like an observer and looking into the black box is really like the point where you get the information out, right? So the other thing too is that, we can be in this scenario for like the entanglement baseballs, like we can be right next to each other. We could be in separate rooms. One of us could travel to another galaxy and it would still be the same thing. So I hope the phone cord goes that far.
Or, maybe they'll have Starlink will be sending 5G messages across the universe. And, well, but it's still not traveling faster than light because it's only traveling as fast as my cell phone can call. Hey, Jamie, what color is your baseball?
Yeah, yeah, I think, like and this is, like, you mentioned, God doesn't play by, roll dice. This is, like, essentially what, Einstein's big discomfort was with quantum mechanics is that it's inherently probabilistic in nature. And so you have this like probability like factor to it, this randomness factor to it that you don't get in sort of a deterministic universe. And wouldn't it be nice if everything was deterministic and like explainable? But sometimes, we have in quantum mechanics examples of that where it's just not, and it is a black box, and then you open it and you get out an answer. So, how do you use that? How do you actually use that to do something that's useful, like in the world, is an interesting question.
Before I ask you about that, I got to sneak this one last thing in, which is that God does not play dice, but God does play baseball. Okay. Okay. Yes, Jamie. So tell me, how do we actually use this wacky rainbow baseball game? How do we actually use it in any way?
Yeah, so I think like in this case, like when we're talking about quantum computing, like the analogy here is like baseballs are qubits, right? And so, you can think about a single qubit, you can think about two qubits and how they interact with each other and again, sort of like this idea of entanglement and superposition that we get when we have an array of qubits. More qubits the better to be able to actually do computation in circuits that are interesting. But certainly, like, I think that it's a really good visual. If you look up like a quantum circuit, usually what it looks like is a music score, right? Where you have each line is associated with one of the qubits. And so when we go in and create a circuit, what we're doing is we're basically, creating a series of gates which are operations that we perform on the qubits to put them in different states kind of purposefully. So oftentimes what you do in the beginning is you just put them all in a superposition with each other and then you tweak it from there. So we like I said, like subatomic particles, right? So you can think about electrons or photons having these types of behaviors. So we at IBM, are looking at what's called superconducting transmon-based qubits. And so really like this is more or less like using microwaves to speak to or to hum to the qubits to put them into these different states as we program the quantum computer. And so effectively what you do is you kind of set that up ahead of time and then like put in your set of instructions. It does its thing in the black box. The qubits, orient themselves in different ways, interact with each other in different ways. And then at the end, you perform a measurement. So whatever series of instructions you put in there, and there's some other tricks and things that you can do mathematically and algorithmically, but, like, at the end of the day, you still need to do this measurement, and then you get out your ones and your zeros.
This makes sense, and I think that like I'm going to bring back the baseball analogy, but
Yeah,
not
bring it back
in a big
around.
way. But yeah, we're going to bring it back. But it's just like if like thinking about these qubits, it's just an object that we're storing information with, right? And so if you can store information on the state of the qubit, or it's meaningful if the baseball is red or blue. And so while it happens in a black box because of these other quantum rules, kind of forbid looking at it, forbid that. But there's like we can punch the box around and do things we know will kind of jostle the probabilities that they become red or blue, or in the case of quantum, that the baseballs will, qubits will be 0 or 1.
Well, so the materials, right, is a big part of this themselves that we use for qubits and how we set them up, and how we kind of, we purposefully select materials that you can manipulate in a certain way with certain things. I mentioned microwave pulses. That's one way to do it, certainly. Qubits tend to be very sensitive to their environment just in general, and it kind of makes sense, like, when you think back on the principles of quantum mechanics as to, like, why this is. But it's doing exactly that. You're putting something into a state, and you're asking it to basically to hold that state. So the material needs to be able to, like, stay in that energy state for enough time that you can run a circuit and run the calculations that you need to. Um, one of the things that we talk about is, decoherence, which is essentially when a qubit falls out of that state or goes into a different state that we didn't necessarily program it to go into. And so in that instance, you can get, errors as in your measurement at the end. So you might get a one where really was supposed to be a zero. And so part of the probabilistic nature of this is we run things multiple times to build up kind of a probability curve, and then you can extrapolate out, like, whether the state is really a 1 or really a 0. Blue or
Awesome.
red?
Blue or
Oh.
red, baseball in my pocket versus baseball in my hand. Well, I think that I know that we are going to go like really deep into the mechanics and the science and the physics of quantum computers in either in an upcoming episode. So I want to talk to you specifically because you know chemistry probably more than anybody I know about actually using these things for simulating chemistry, right? So I want to know from you, like, why would we want to simulate chemistry? Can't we just do chemistry?
Yeah. So, my background actually, so my PhD is in organic chemistry, and I was an experimentalist. So I was actively working in the labs and combining things together in flasks. And, we have a whole, century worth of sort of proof points over time to say that, when I combine these two things in a flask, I'm going to get out this, product that I expect. Right. Well, sort of in the same way that, it's everything's probabilistic when it comes down to, like, how nature behaves, like, sometimes you don't get what you think you're gonna get, and sometimes you put things together in a flask and you get out something totally different, and you do sort of the characterization of it, the spectral analysis and, like, all that, and you find, like, this is something totally different than what I was expecting. So when that happens, we need to try to figure out how to explain it, and you have to go back to quantum mechanics to explain it. So a lot of the theory that we've developed over time is, fundamentally based in quantum mechanics. You need to be able to describe, in an atom, you have the nucleus, you have the core, you have protons and neutrons, and then you have, we've all seen these rings around it where the electrons sit in different discrete energy levels. They can't sit in between, so this is how you can, in some part, describe the behavior of molecules and of atoms. And so we need to apply that to be able to figure out, like, what we made and then, like, explain it so that we can have that as a part of our body of literature and understanding of how chemistry works so that the next future generations of experimentalists can then pick it up and go with that.
This is like the classic conceit of quantum, right? I mean, we're at, chemistry is this innately quantum thing. So we want, and so therefore, and to quote Mr. Feynman,
Yes. Yeah.
nature isn't classical, dang it.
Yeah. So that's exactly right. So, like, for me, like, coming into quantum, like, as quantum computing, like, with my chemistry background, a lot of it was made sense to me just because I've had so much experience over time with hands-on chemistry that it just, like, yeah, like, for example, in transition metals, we have a lot of electrons. Electrons, interact with each other. But when you have an entire, like, a large amount of electrons, it's really difficult to be able to, like, predict how a metal is going to behave. And part of it's because the electrons themselves are so highly what we call correlated, right? So when we develop out sort of the models from a lot of it has been classical to date, and now we're starting to look at, quantum, descriptions of these as well. But, like, when we look at the models, it's very difficult to describe all of those electrons and their behavior. Like, you can describe maybe a single electron and then, like, make approximations for, like, that electron sitting in, like, a field or something like that. But you don't really have the opportunity with classical computers and classical approaches to be able to describe all the electrons at once, right? Sounding a lot like entanglement. So I think that that's where, for me, like, it was a no-brainer that, like, bringing in, quantum computing as a computational tool, especially for, describing molecules, behavior, chemistry, and quantum chemistry at its core, just makes a lot of sense, because you're using a system that has similar properties as the system that you're trying to describe.
So why weren't classical computers like why where do they falter when they're trying to simulate this mess of electrons?
In classical, right, you have these limitations of, like, ones and zeros, and so effectively what that means is that you can do, like, 1 electron and then model it with the 2nd electron. You can take the 2nd electron and model it with the 3rd and the 1st, but as you can imagine, like, if you keep doing that over and over and over again, you get to a point where you just have, like, an astronomical amount of computational resource that you would need to be able to describe that accurately as you're trying to do, like, all of these sort of, one by one kind of descriptions, right? So, that's where the hang up really has been, is that you can't get to very large systems and do it in an exact fashion. You have to start applying all of these approximations. You have to start looking at it and doing sort of hand wavy descriptions of the system. And when you do that, at the end of the day, like, the sort of description of the system breaks down because it's no longer really, like, describing all the different pieces of it. It's just describing, like, one part of it, and so that leads to some really, from my perspective as a bench chemist, right, some very inaccurate, kind of answers. And so it's very time consuming, as a result, and takes a lot of experimentation to, like, validate any kind of description that we have and any theory that we have. And boy, wouldn't it be nice if we had something that did a better job of it and wouldn't take as much time to, like, validate, but rather, gets much closer to the actual, what you're observing in the flask, in a much shorter time. I think that would save a lot of people's time. It would save a lot of money.
So how would it actually look like to simulate them on a quantum computer? Like how does that look different? And I know you got into it a little bit before, but is it just like one qubit is one electron or is it a little bit more involved than that?
You can think of them as spins. So when I do, like, back of the envelope calculations of, like, how many qubits would it take to simulate, this molecule, you can just go by sort of the molecular orbitals and then, like, the spins, that, like, spin up, spin down for each of the different orbitals and can lay it out that way. Of course, there's other mathematical tricks. I don't think, from algorithm and design, you don't necessarily have to stick to that. So sometimes you have things that are, for example, like, redundant from an energy level, and you can kind of just say, like, these two are redundant, you can count it as one. So there are different ways to make the problem size smaller, but just, like, from a very, like, just back of the envelope, like, high level description, that's how you can describe a molecular system onto a quantum computer, is by thinking about the qubits as representing spins for the different orbitals in a molecule.
When you say spins, this is the spins of the electrons in those orbitals, or is it a little bit more involved than that?
Spin up, spin down.
Spin up, spin down. All right.
Yep, yep, and so
Cool.
you just, yeah, you just treat each of those, and again, like, there's all sorts of different ways that you can kind of leverage quantum computers to describe, molecular systems, but at its core, and when, you're thinking about, like, what Feynman was, like, really envisioning when he was saying that you needed to use a quantum computer to study things that behaved quantum mechanically. That's what he was thinking of. It's like a direct mapping of the system onto the quantum computer. So that's that's at its heart, like, where that came from, and then we've advanced things past then to be able to describe, and model a lot of different things, molecules definitely being one of them, but, materials, all sorts of, different types of systems, with similar ideas, but with twists.
And we can do that now? Or where are we with doing that?
Yeah, actually, I mean, I'm so impressed at how far we've come. It's amazing. No, it really is. I remember the first time I ever saw a, like, chemistry example when I was walking through the halls of Yorktown Heights, our headquarters for research, right? Usually chemistry didn't show up in the hallways, but it was Abhinav Kandala was, showing that he could use a quantum computer to measure the ground state energies of a small molecule at the time. There were only like 2 atoms in that one or 3 tops, right? That was, 8 years ago now, and, like, in that time, we've now evolved and into being able to do, like, larger and larger systems, and just recently, we actually reported on being able to do an iron complex, which to me just, like, is amazing, especially because those are the hardest ones to describe, classically, um because of the amount of electrons. So as soon as you get into those transition metals and metals in general, like those are the hardest to describe, and we did that last year. So I think like, and now granted that was with HPC plus quantum, which I think is really important. So it's not just quantum alone, but you have quantum computers doing, a piece of the calculation, and then, classical computers doing another piece of the calculation. And I think you're going to need both of those for different parts of it for the unforeseeable future. Um, but I will say that in that instance, those were getting closer to exact values than I've seen. And it's far beyond the reach of what we can do classically to get to exact values. So, like, in other words, the system sizes are significantly large enough that you can say this is something that is distinct and that we wouldn't be able to do on a supercomputer by itself.
Cool. So I want to sit with this one for a second, right? Because what you're saying is basically that classical really struggles with these metals, these iron molecules, right? Our best classical simulations can't exactly tell us what to do. And even though quantum is kind of in its just getting, moving from the lab into the real world phase, it's been doing that for a while, but let's just say it is now still kind of new. We're already at this point where quantum kind of assisting classical in doing this problem is better than classical alone. So classical can't get an exact answer, and quantum and classical can get a pretty good answer, right? And then how does that compare to like the classical best answer that we can do, that we can do? So we can't exactly do it, but we can still it's still kind of a race, right?
Well, yeah, and so here's like kind of the beauty of when we think of something like a ground state energy is that because of the nature of what it is, the lowest number wins, like, no matter what. So if you're able to get, like, some value, if it's, like, lower than another value, then you can basically say it's an improvement, right, in sort of the way that it's modeled. So that is, I think, what we're looking at and we're kind of using to validate what we're doing here and to do exactly what you're saying. It's like to show that you're able to get something a little bit better, a little bit different, a little bit more descriptive, using a quantum computer in concert with high performance computing, in concert with a supercomputer, right? And than you would otherwise. And I wouldn't say that we're, like, perfect yet on that. I think that we're continuing, like, to evolve the algorithms, and it keeps getting a little bit better, a little bit better, a little bit better, a little bit closer to that lowest value, as you can get. And then as those algorithms continue to evolve, that's when we're gonna start seeing closer and closer to Zach. Now, I will say, for me personally, this does become a little bit of a philosophical quandary because at what point do you stop? Because if we can't get exact values anymore in a classical, like, supercomputer, what are we comparing it to, right? So there's gonna be a certain point in time where we're no longer gonna have, like, an exact value that we can say, "This matches that," right? Or it's within some amount of energy from that. And at some point in time, I think we're just gonna get back into the mode that we've been working in computational chemistry for a long time, which is that you need to compare it to experiments. And so, like, how close do you actually get to the values that experiments produce, and like, how accurate are you really? We're not there yet, but that's just kind of like I'm seeing that, like, this progression, and, like, I think even now, like, with these iron sulfide complexes, like, you have to kind of question what is the best state of art classical that we are comparing it to, and where is what is the like real answer that you're like using to validate?
This is cool to me because if we, stick with this, right now, we kind of have a lot of faith in our classical simulations, right? That we're using all these supercomputers to exactly do this math. And so, of course, we have to sort of verify and validate what's happening, but, we're feeling pretty good about it. But as quantum kind of comes onto the scene, it's almost like we're using quantum to like create hypotheses, right? Like quantum said that this is how it would work. And so now we can then go into the lab and then validate with real chemistry what the quantum computer said. And that's just going to keep happening until we're at this stage where we're like, hot dang, quantum computing is like really creating cool stuff.
Yeah, I mean, the holy grail, right, is like to have predictive, what I call in silico, capabilities. So in silico, in silicon, like computational capabilities, right? So that is ideal. Like, what if we flipped it on? And I'm, again, just talking about chemistry, but I think it's like, a near and dear example to me. But if were able to flip it on your head, so it's like there's not as much experimental work that needs to occur first, but rather you were like running something like on a computer, right? That then gave you an answer that you had a lot of faith in. Like you really like had a lot of trust in that because you've seen it tested over time and it's giving you the correct answers over a long time. It would either dramatically reduce the amount of experimentation that would need to accompany that to validate it, or in some like, in theory, potentially just like you wouldn't have to do any experiment, right? You just trust what the computer's telling you. We are very far away from that. I've gotten some really weird answers, like out of classical, like really weird. So we have a long way to go, but that's what we need to get to. That's exciting.
And can you tell me then, with all of this excitement, just like take yourself back into the chemistry lab and imagine what you would have done if you had access to, like, how would you actually be using the quantum computer, and how would you actually like be getting excited? Like, what would you be doing? What would it look like?
Yeah, I mean, if I so and actually my lab that I worked in as a graduate student was actually at the time very ahead of the curve because we had computational chemists that sat with us. Like so we had the lab and then there was like a room that was like full of computers and people would run calculations and simulations for us to help us describe as we were going, what we were seeing in the flask. So in situ, right, in the flask. And so that I think is an example. Like, so if we had quantum in principle, right, like it wouldn't look all that different. Like if you're looking at and thinking about like the software as it continues to develop out, say someday there's a software that's a chemistry software, some package that we use, looks very familiar to us. We put in the molecules that we're thinking about combining together and whatever else we want to include, like the solvent maybe, or a catalyst, or, whatever it is, like heat, accounting for heat in the flask or cooling. And you put all those like parameters in and then you press enter and it gives you here is the result. Like here's what you can expect. Even better if you could, like, give the answer and saying, like, "Here's the drug I wanna make because I know that it cures this disease. How do I make it?" And just, like, put that drug in and then, like, have it back calculate out. So those are the kinds of things that I think would be extremely useful. Or, like, if you have something fail, and have it be able to tell you, "Well, obviously, you should have cooled it to -20 degrees. What were you thinking?" You know what I mean? Like, that's the kinda thing that I think would be extremely helpful. So, you can imagine it sort of like what people talk about with AI is like augmenting, right? Like the experience of like someone who's in the lab. And then, again, like if you get to a place where it's really predictive, then in principle, all of it could be automated, which would be really cool too. Because then you can think about curing diseases and, you know, like being able to transform, yeah, catalytic designs and all sorts of things. So anyway.
Well, this perfectly transitions into the question I like to ask all of our guests at the end, which is just, so what do you want a world with quantum computing in it to look like?
Yeah. I mean, so I think we've already shown that there's definitely evidence for it being a scientific tool and something that can help with research, right? So I think that that is like the starting point. In the future of quantum, I think that what I would love to see is like an impact on the world in a positive way. So, an impact on society in a positive way. So, if we can lower, energy consumption for certain industrial processes, lower CO2, emissions, um, like help cure really difficult diseases. These are the kinds of things that, like, in a big picture, and I'm not trying to just like have that be like the grand vision and say that it's so easy because it's not. I think there's a lot of innovation that has to happen, like, in between now and then. But from my view, like, the best parts of science is when it helps benefit humanity, and that's what I view quantum as doing, as it's also being integrated into an everyday scientific discovery.
I think a lot of the listeners are kind of being hit with a lot of new topics and a lot of ideas, which we're obviously going to be fleshing out throughout the season. I'm really excited to do so, but I would love just from you to give us like a final wrap up of like what should people take away from this when it comes to understanding quantum, understanding the world with quantum, and then actually using quantum to simulate the world with quantum.
Um, let me think. So, takeaway. Quantum computers operate on principles of quantum mechanics. The world, nature, operate under the same principles. We can use quantum computers then to model and to describe our world in a way that we would not normally be able to do using classical alone.
I love it. That's great, Jamie. That was awesome. I really appreciate you coming in to talk with me today. And I hope that we can continue this conversation and have you on again soon. Yeah, thank you so much. This was awesome.
Thank you, Ryan.
That's it for this episode of The Coherence Times. If you enjoyed the conversation, please be sure to subscribe wherever you get your podcasts and share it with somebody who's curious about quantum. You can find us at Spotify, Apple Podcasts, and YouTube via the IBM Research Channel. And for more episodes, resources, and deep dives, please visit us at ibm.com/think/podcasts. I'm Ryan Mandelbaum. Thank you for tuning in. And remember, the quantum future isn't just coming, we're building it right now.